In this video, we're going to examine a problem where there's a drag force exerted on a projectile that's fired vertically. So the problem I have written here says a 2 kilogram mortar shell is fired vertically upward with an initial velocity of 80 meters per second. Suppose the shell experiences a drag force from the atmosphere equal to Fd equals cv squared, where c is a constant and v is that vertical speed of the mortar. Find the maximum height of the shell if c equals 0.03. So for a particular value of c and a given initial speed and mass of the mortar, can we determine how high up that mortar will go, the maximum height of the mortar, while it experiences this drag force? So can we examine the motion of an object where it experiences a force that is a function of the velocity of the object, right? That drag force is dependent on the square of the velocity. The first thing I'd like to do is draw a free body diagram for this mortar. I know that the mortar experiences two forces as it moves through the air. One of those forces is the weight, and I'll just label that force vector mg, where m is that 2 kilogram mass of the mortar shell. And the other force that the mortar experiences is that drag force. And I happen to know that that drag force points downward, and I'll label that Fd. So how do I know that the drag force points downward? Well, if the mortar shell is fired vertically upwards, then its initial speed points upwards, and if the velocity is upwards, that drag force will oppose the motion of the object, and so it will point downward. And so both the gravitational force and the drag force are opposing the motion of the object, slowing it down as it goes up. And so now what we should do is use the free body diagram to create a Newton's second law net force equation that starts to relate the motion of the object, whether it be the speed or the acceleration, to the forces that it's experiencing. And so I'll start by writing the net force in the y direction is equal to the mass of the object times the acceleration in the y direction. And the two forces that act on this object, both mg and fd, point downward, and I will call that the negative direction. So minus mg minus fd equals the mass of the object times its acceleration. And that acceleration will be some function of the velocity once we substitute that in with a drag force. From here, the next step that I'd like to take is I would like to plug in some of the numbers that we know. So the mass of the object is 2 kilograms times g. That's the first term in the equation. And so 2 times g, if g is 9.8, 9.8 times 2 gives us 19.6. So the first term is minus 19.6. The next term is the drag force, and the drag force is 0.03 times v squared. And we don't know what v is. It's a variable that will change with time. And so we will write that as minus 0.03 times v squared. And on the right-hand side of the equation, I do not know a. In fact, what we're trying to do is build an acceleration equation that depends on the velocity. And so I'll just plug in the fact that I know what the mass is, and that's 2. So 2a. So at this point in time, I'd like to divide both sides of the equation by 2. And so I'm just plugging in and simplifying as much as I possibly can here in order to get an equation that I can work with. And so if I divide both sides of the equation by 2, then I get that the acceleration of this mortar shell is given by minus 0.015 v squared minus 9.8. Whenever we are in this sort of a position where we have an acceleration equation that depends on the velocity of the object and not time, right? Typically we're dealing with acceleration equations that depend on time, where we plug in a particular instant in time and determine the acceleration. But here the acceleration is a function of velocity. Whenever we're given a problem like this, there's a little bit of a trick that we can employ in order to proceed and answer a question like this. And so it looks something like this. I know that almost by definition, velocity is given by displacement over time. And in this instance, in terms of differentials, I can write that as dy over dt. And acceleration, by definition, is velocity over time, change in velocity over change in time. And in terms of differentials, I could write this as a equals dv dt, right? And I'm not writing dvy because the object's only moving vertically, and in the problem statement it said that the velocity in the vertical direction was given by v. So what I'd like to do is take both of these expressions, solve them for dt, and set them equal to one another. So on the left-hand side, I have dt equals dy divided by v, and on the right-hand side, I have dt equals dv divided by a. And so now if I set these two expressions for dt equal to one another, and simplify it a bit so I'm not looking at the fractions, then what I'm left with is a times dy equals v times dv. And what this will allow me to do next is, first I'm going to substitute in my equation for the acceleration into this expression, right? On the left-hand side I have a times dy, and on that left side I'm going to plug in my expression for the acceleration. Right, so I have minus 0.015 v squared minus 9.8 times dy equals v times dv. And what I'd like to do next is separate the variables, right? So move everything that involves the velocity to the right-hand side and leave the dy on the left-hand side, since all of these other terms include v. And so what that looks like is dy equals v divided by the expression for the acceleration, so minus 0.015 v squared minus 9.8 times dv. And so what we've done is we've started with a free body diagram for this object. From that free body diagram, we were able to write a Newton's second law equation for this object. I wrote generic equations for velocity and acceleration, solved them both for dt, and set them equal to one another. And what that allowed me to do is separate the variables in a way that will allow me to integrate to determine an equation for position. Right, and I've just said a lot there, but we were asked to determine the maximum height of the shell for a particular instance. And so what we really need to do is determine a position. And the only way that I can incorporate position is by making the substitution that I've made here in red. And so now on the left-hand side of the equation, I have dy, which can be integrated to solve for a position. And on the right-hand side, I have v dv and my acceleration equation, which only depends on v, right? That was my original starting point. I said that the acceleration equation only depended on the velocity. It was a function of the velocity. And so now what I can do is I can take this equation in red and I can integrate both sides with respect to the variable on that side, and hopefully end up with an equation that will allow me to determine the maximum height of this object. And so really, for the rest of this video, this is the equation that I'll be working with in order to determine what that height is. Alright, so what we need to do next is actually set up the integrals on both sides. I'm asked to find the maximum height of the shell. And so what I'm going to do on the left-hand side of this equation is I am going to integrate the left-hand side of this equation, where what I'm integrating is just dy, or 1 times dy. I will integrate from the initial height, the starting height of the object, which I will call 0, to the final height of this object. And the final height is going to be that maximum height that the shell reaches. And I'm going to call that height h. So the object will travel from 0 to h in height. And on the right-hand side of this equation, I need to perform an integral where on this side of the equation, I have the initial and final speeds. And so given in the problem, I was told that the initial velocity was 80 meters per second. So that is my starting point. And so the limits of the integral are defined such that, right, when the height is 0, the velocity is 80 meters per second. And then for the top limit, when the height is h, what would be the velocity? When the object reaches its maximum height, the velocity would be 0, and so the top limit on this integral should be 0. And so the left-hand side of this equation is fairly trivial, but the right-hand side will involve a little bit of work because the equation that I need to integrate is v divided by negative 0.015 v squared minus some constant 9.8. And so now my job is to figure out how to integrate both sides of this equation and solve for that height h, that upper limit of the left integral. All I've done is I've taken the equation from the first slide and I moved it over here without changing anything. The first thing I'd like to do is evaluate the left-hand side. The integral of 1 times dy is just y. And when I plug in the top limit h, and I subtract plugging in the bottom limit 0, h minus 0 just gives me h, right? So the left-hand side of this equation is just h, and that equals the whatever the integral of this right-hand side of the equation is. And so I would like to start on the right-hand side by making a couple of adjustments. I'm going to take out a minus sign because in the denominator of this equation I have a couple of minus signs. So that'll make everything positive. And then I would also like to write those two numbers in the bottom as fractions. Because once I start to think about how to make some substitutions to perform the integral, I think having them as fractions makes it easier for me to understand what's going on. So I'll write the right side as minus the integral from 80 to 0 of v divided by, and 0.015 as a fraction is 3 over 200, so 3v squared over 200 plus 9.8 as a fraction is 49 over 5. So 3v squared over 200 plus 49 fifths dv. What I'd like to do next is I'd like to solve this integral by u substitution. And I would like to let u be the entire denominator of the integral. Right? And so what we're going to do is we're going to define u as 3v squared divided by 200 plus 49 fifths. And if we do that, then the derivative of u with respect to v, so du dv, is equal to 3v divided by 100, right? Because the second part of u, that 49 fifths term, doesn't have v in it, and so that would just drop out. And the first term of u, if I take the derivative with respect to v there, then the squared would come down and make 6 over 200, and 6 over 200 is the same as 3 over 100. And then of course I would subtract 1 from the exponent and just have v. So du dv comes out to just be 3v divided by 100. And so if I rearrange this, I have dv equals 100 divided by 3v du. And remember, the reason why we take this derivative and then rearrange it is because we then plug it back into the integral in order to perform an integral with respect to u, right? And so now what I have is h equals minus the integral from 80 to 0 of v divided by u, right? Because the entire denominator was defined as u. And instead of dv, I write 100 divided by 3v times du. And hopefully you see the simplification, right? We have minus the integral from 80 to 0, and the v on top and the v on the bottom cancel. And what I'm left with is 100 divided by 3 times u, right, where that u is in the denominator. And so, of course, this could be simplified where that 100 over 3 is a constant, and I can pull that out. So minus 100 over 3 times the integral from 80 to 0 of 1 over u du. And unlike the integral that I have in the top left, this is an equation, or sorry, this is an integral that I can handle, right? 1 over u, the integral of 1 over u is just the natural log of u. And so I could write this as minus 100 over 3 times the natural log of u evaluated at 80 and 0. And so really what I would need to do next is plug in what u is, of course, minus 100 over 3 times the natural log, and now instead of u, I'll write the expression from up above, right? We defined u as 3v squared over 200 plus 49/5, evaluated at 80 and 0. And so really, to determine the maximum height, I need to plug in 0, the top limit, into that expression, and then plug in 80 into that expression and subtract. And whatever my answer is should be the maximum height that this object reaches. So I have h equals, and first I'm going to plug in 0. And when I plug in 0, the only place where I have to plug in v is in the first term inside the natural log. So plugging in 0 there means that I get minus 100 over 3 times the natural log of, and that first term will drop out because it's 0, the natural log of 49/5. And so when I plug in 0, that is what I get, minus, now I need to plug in 80. And so what I get here is minus 100 over 3 times the natural log of 3 times 80 squared divided by 200 plus 49/5. So the natural log of that. And so this last line here is quite a bit of a mess, but really I just need to type this into my calculator at this point. And I think what you will find is, although it looks a little messy, what I get for the first part of this equation, in the first set of brackets, is I get minus 76. And then I have the minus sign between the two sets of brackets. And for the second set of brackets, and I recommend that you do this for yourself, I get negative 155. And so negative 76 minus negative 155 comes out to be about 79 meters. And so based on the integral that I've set up, the height that we should get should be the maximum height reached by the projectile. And so for an object that experiences the type of drag force that was described, if it has a mass of 2 kilograms, and if it's launched with a vertical speed of 80 meters per second, it should reach a maximum height of about 79 or 80 meters. And now, what I'd like to do is I'd like to compare the maximum height that it reaches in this first case to the maximum height it would reach if it didn't experience a drag force at all. And the reason why I think that that is valuable to a student who's doing a physics problem is a lot of the times the problems that we solve ignore things like these drag forces. So here you can see how the problem becomes quite a bit more involved if we try to incorporate a drag force into the equation, right? We have to perform integrals on both sides of the equation and do U substitution, and it becomes quite challenging to figure out that maximum height. But now let's consider the situation where we start this same problem over, but we just say we have a projectile launched vertically straight up with a velocity of 80 meters per second. What would be the maximum height if it experienced no drag force? I think if that was the problem we were trying to solve, we could start with the kinematic equation Vy squared equals V naught y squared minus 2g delta y, where delta y is the final height minus the initial height. And we know, of course, that if the object experienced no drag force, it only experiences the force that, that downward acceleration from gravity, which is slowing it down. And that force alone is going to take a little bit more time for it to take all of the energy out of that ball in order to slow it down to zero speed. And so you should expect that the height here be a lot higher. But still, at the maximum height that the ball reaches, regardless of the situation, its velocity will become 0. And so let's make the final velocity 0. And let's make the initial velocity the velocity that the object has, 80, and it should be squared. Minus 2 times 9.8 for g. And again, we're going to let the initial height be 0 and the final height be h. And so when I solve for this, I think what I get is 19.6h equals 80 squared. And so the maximum height of the object is 80 squared divided by 19.6. And so when I solve this without the drag force, 80 squared divided by 19.6 is much bigger than 80, right? It comes out to be about 327 meters. And so now we can really see the big difference that I was trying to point out. If we ignore the drag force and just say we have a projectile fired at 80 meters per second straight up, it goes something like 327 meters. But if we incorporate some sort of realistic drag force that accounts for the atmosphere pushing on the projectile as well, then we really only get a height of 79 meters. A big difference based on one simplifying assumption that we make about the object as it moves. Hopefully, looking at this example helps you understand how the drag force can complicate things, but also provide a more realistic description of how to solve a problem like this.